a little hollow circle usually. And so that's the general form. Now here's a more specific form. The set n in this case here is the natural numbers, n, right? Big N. And the binary operator is defined here. It's the HCF, that stands for highest common factor, right? So you take any two members of natural numbers, I know, 2 and 4, let's say, okay? And you're asked to find the highest common factor of those two numbers. Well, what is the highest common factor of 2 and 4? Well, it's 2, right? It's not 1.5, or, well, it can't be, because it's going to be a natural number, a counting number, okay? Now, the result is always a natural number, okay? And you get one and only one result. You do get a result, and it's one and only one. And it's also a natural number. Therefore, this binary operation on this set, it depends on the set, of course, is closed. Now, what about this one? So your set here, in this case, is the integers. So 0, plus minus 1, plus minus 2, plus minus 3, da, da, da. So the set of integers, the binary operation in this case is just subtract the minus sign. That's a binary operator. You need to have two numbers if you're going to subtract something. Okay. Now, is that a closed operation? Well, if a and b are both integers, and you subtract one from the other, you still get an integer, right? Common sense. Therefore, this binary operation on this set is closed. Okay? So closed, closed. Now, interestingly, the order. Now, let's say this is 3 and this is 7. Two integers. So 3 minus 7 is not the same thing as 7 minus 3. So in this case, the order is important. So you can talk about an ordered pair, like A, binary operator, B. Now you have a pair, you have two members of your set, and the order is important because A operator B may not be the same thing as B operator A. Okay? So you can talk about an ordered pair, where a pair that is ordered, A before B or B before A. The order is important. Now, if it can happen, if for any pair in your set, if A operator B is the same as B operator A, if that's true for all pairs, right, then that operator is said to be commutative on the set. To commute, like, means to swap around the order. If AB is the same as BA for all pairs, then that binary operator is commutative on the set. Now, this too will feature in group theory. So this lecture is giving you a lot of vital tools that we'll come back to in 2 lectures' time when we're talking about the nature of groups and the definition of groups. Okay? All right. Now let's take any 3 elements or members of the set S and perform on them 2 binary operations. It's the same. Sorry, I better be clear here. You're performing the same binary operation on twice. Like, for example, let's say it's add. Your binary operator is the plus sign. So this would be like plus, plus. Or if it's the minus sign, then this would be minus, minus. Okay? Now, question. If you take A and B first and operate on them with a binary operator, and you get a result, and then you take that result and you operate on it with a binary operator with a third member, C, right? So that the result you get there with two binary operations, will that be the same as this way, where you take the second and third, operate on them first, get the result, and then operate on the first member, A, and that result? So is that true in general? Well, for groups it will be. I'm jumping ahead a little bit. But there are algebras where this is not the case, which is interesting. Also one of my personal interests. If you're an algebraist, when this kind of phenomenon does not occur, can be quite interesting. Yeah, again, you get very rich structures. Okay, now for groups, for example, if doing this is always the same as that for all possible triples, for any random three elements of your set, if A, B, C is the same as A, B, C, so A, B, C is the same as A, B, C, then that operator is said to be associative on the set S. Okay? So if you take any three elements of your set and you perform two binary operations on it like this, so you put these two first, or on the right hand side you put the second and third first, you operate on them first, then if the result, left hand side, is the same as the right hand side for all triple combinations, for any three elements of your set, then that operator is said to be associative on S. Now, why this word associative? Well, to associate means sort of like come together. Like an association is like a group of people. They've come together to do something, right? So, when you're associating pairs, like here you're associating A and B, and you're putting them together and operating on them. And here you're associating B and C in a sense. Okay? So if you have a binary operator on a set S that's associative, in effect you can forget about these brackets. It doesn't matter, because if this is the same as that, then the brackets become irrelevant. So you can just forget about them for associative binary operations. All right, now have a look at this particular pair. So you've got the set, remember here's the general form, the set S and a binary operator, a little circle. That's the generalized form. So here's more specific. So in this case down here, your set S is the set of integers, Z, right? And the binary operator in this case is just minus, right? The subtraction sign. Now that combination, that binary operator for that set, is it associative? Well, let's try something. Now remember the binary operator is negative, so let's try something like this. So we'll choose A, B and C. 7, 4 and 2. Will that work? Let's just try it. So 7 minus 4 minus 2 equals 1, right? And 7 minus 4 minus 2. So that's 2, that's 5. Okay? So this particular binary operator for that set, the integers, is not associative, because look, we got a difference, right? They're not the same. So be careful. All right, let's move on a bit. I'll clear a bit of space here. Okay, the concept of a table. A binary operation table for a finite set, and let's say a small finite set, because if it's large, the table gets too large. But here's an example. I'll draw it again to make it a bit bigger, but